Give it just another minute for a couple more people to sign on, and then we'll get started. Okay, so good morning. I hope everybody's doing well. I am coming in from Folly Beach. So I'm gonna do this and then hopefully go back out and hit the sand, water for a little bit before we get this tropical storm that's coming in. So we are continuing on with chapter 6. Hopefully if we can get through everything today, then we don't have to meet on Thursday, which is the goal. So we left off talking about, where were we? We didn't quite get to this part. Right, okay, yes. So we had talked about, morning, Michael, the idea of you can have multiple parts within a whole. So one spider can have 8 legs, one chair can have 4 legs, one water molecule has 2 hydrogen atoms. And we realized that this formula that we're looking at is a molar relationship. So it tells us how many moles of one thing we have to how many moles of another thing. So if I have a formula, just write out a new one here, such as aluminum sulfate, Al2SO4 3. There is a built-in molar ratio within this formula. It says that for every 1 mole of the entire compound, which is Al2SO4 3, we get 2 moles of aluminum. What else do we have packed away in here? We have 3 moles of sulfur because the 3 gets distributed to both things. So 3 moles of sulfur. And we get 12 moles of oxygen because we always want to multiply our subscript formulas within the formula. So this is the ratio. So let's say that your given information says that you have 55 moles of Al2SO4 3. And well, I want you to find moles of aluminum. Well, there's a built-in ratio. It's this here to this here. let's not make that line so long, this here. So these two components, do I use these? Not for this given problem. It's not asking us about sulfur. It's not asking us about oxygen. It's just saying, hey, what's the relationship between aluminum and the compound? So my single conversion factor for this problem is 1 mole of the aluminum sulfate. Sorry, that should be a 3. Is it going to yield 2 moles of aluminum? So we're going to just set this thing up in dimensional analysis, which tells us that anytime we do dimensional analysis, we start with our given information. In this case, it's 55 moles of the compound. And we're going to use the conversion factor. Now we want to get, and let me actually specify this as moles, aluminum moles. We want to get into moles of aluminum. So I'm going to put that on top. So 2 moles of aluminum go on top for every 1 mole of Al2SO4(3). So it's a 1-to-2 ratio, right? 2 aluminums for every 1 compound. So the compound will cancel, and we take 55 and we're just going to multiply it by 2 for a total of 105 moles of aluminum. So in 55 moles of aluminum sulfate, we have 105 moles of aluminum. If you're like, well, how can you have 105 moles within 55 moles? Remember, these are talking about moles of different things. This is 55 moles of a really big, clunky compound. This is 105 moles of just an element, aluminum. So I want you to do the same thing using the same ratios, but let's change the numbers up just slightly. 100, yes, 110. Yes, 110, not 105. That's why you can't leave me to do math without a calculator. Even though I do have a minor in mathematics as well, but when you start to get into higher math, you just calculate everything. So given, we're going to go with, let's say we have 13.8 moles of the aluminum sulfate. And I want you to find how many moles of oxygen are in 13.8 moles of aluminum sulfate. We're going to use the same ratios, well, similar ratios. I'll give you just a minute for that. Okay, so in this ratio, we're going to look at the compound as a whole in relationship to the oxygen. So it's a 12-to-1 ratio. We start with our given information, 13.8 moles of the Al2SO4(3). And I know that for every 1 mole of that compound, the Al2SO4(3), and you want to get in the habit of like labeling your moles. because, you know, you want to know, are you talking about moles of one thing or moles of another thing? So keep labeling those. So for every 1 mole of that, we're going to get 12 moles of the oxygen. Why is it 12? 4 within the parentheses, 3 without the parentheses. We multiply those together to give us the 12. Okay, so we're just going to take that 13.8 moles of aluminum sulfate and multiply it by the 12 mole ratio. And we get 165.6, but we only get to use 3 sig figs. So I'm going to round that to 166 moles of oxygen. So let's look at that flow chart that we had from the other day. This thing right here, remember this, where we had grams of the element into moles of the element to atoms, and then we had the compound. Now we have a bridge between going from the moles of the compound into the element, individual element, or element into the moles, right? That's the molar ratio using your subscripts. So let's add here in this arrow, and it's getting kind of cramped, but we're going to put the subscripts from formula. Subscripts from formula. Same thing here. So you can add another arrow between these two here, between atoms and molecules or molecules and atoms. This also is the subscripts from formula. So if you had like, hey, I've got 55 molecules of water and I want to know how many atoms, you could use the subscripts as well. So those are applicable in either way. But in your flow chart, do you see this place here where we go from grams of element to grams of compound or vice versa? I want you to put like a big red X there. You cannot go directly between those two things, okay? There is no quote unquote easy way to go from like grams of a compound into grams of an element, or at least a one-step way. Instead, you're gonna have to work, kind of backtrack through the flow chart. So, and how often are you given moles of something and you want moles of something? Very rarely. Usually you're given grams of the compound and I want to know grams of the element. You're going to have to do a 3-stepper here. And the flow chart, which I'm going to pull out here, which you can see in this, is going to be grams of compound into moles of compound, and then from moles of compound into moles of the element, and then moles of the element back into grams of the element. So grams of compound, and this is sort of a general flow chart for the next couple problems. So grams of compound, whatever that compound happens to be, into moles of compound, into moles of element, and then we take that back into grams of element. Now, this shouldn't be anything revolutionary. This is in our flow chart. I mean, this is just this limb here stretched out, okay? So you know how to do each one of these steps. We have, we've done every one incrementally. We just haven't combined them together. So let's fill these little arrows or hopscotches in. So how do we get from grams of compound into moles of a compound? We use molar mass of the compound, right? Easy peasy, we've already done that. How do you go from moles of compound into moles of an element? That's what we just did. So that's the formula subscripts. So formula subscripts, or the mole ratio. Sometimes you'll see it as mole or molar ratio. And then how do we go from moles of an element into grams of an element? That's just the molar mass of the element. Right? Don't want to mix those molar masses up. When you're converting within a compound, use the compound molar mass. When we're doing the element side, use the element mass. So there is, again, there's no fast track way to go from here to here. You've got to hop through moles, because the mole is that, again, chemist's crossroad. It's what allows us to kind of morph from one thing to another. So let's do one of these problems together. And then, I don't want to clear you all off. And then we'll work on one on your own. So say how many grams of sulfur are in 12.7 grams of disulfur tetraoxide. Do a little nomenclature in there as well. So I'm given that I have 12.7 grams of this thing, disulfur tetraoxide. It isn't useful when it's in its word form, right? I need to know what the subscripts are to do any sort of converting. So let's write his formula. Disulfur means I have 2 sulfurs. Tetraoxide means I have 4 oxygens. So oxygen with a 4. You need to get those right because I need to be able to figure out what the relationship is between sulfur and the compound. I'm trying to find grams of sulfur. So this general flow chart that we have here is what we're going to follow. Grams of compound into moles of compound into moles of element back into grams of element. And I'm going to even customize that so that it applies just to this problem. So we're going to go specifically from grams of the disulfur tetraoxide into moles of the disulfur tetraoxide. Then from that, we're going to go to moles of sulfur. And then from moles of sulfur, we're going to go to grams of sulfur. So we need to figure out what the molar mass is of sulfur tetraoxide. And I totally don't have a formula sheet on me, so I'm going to do the best I can. All right. So we've got sulfur, which is what, 32.06, something like that, times 2, plus oxygen, which is 16 times 4. So 100, I got 128.12, somewhere around there. So 128.12 grams per mole. This middle step here, this is the way that we convert the magic step that gets us from the compound to the individual element, where we look at the subscripts. So for every 1 molecule, how many sulfurs do we get? You just look at what it tells you. You get 2 sulfurs, 2 to 1. So 1 mole of the S2O4 will yield 2 moles of sulfur. In this very last step here, we're going to just use the molar mass of sulfur, which is 32.06 grams per mole, specifically for sulfur, and this is specifically for S2O4. Is everyone seeing how this is kind of coming together? It's a little bit more work to go from grams of one thing into grams of another, but it will always follow this system. So it doesn't really matter what compound I give you. It doesn't matter what element I want you to calculate for. It's always going to sort of follow this. So let's plug it in. So we start with our given information. And as you get better at this, how did I get the 128.12, Andrea? That is the mass of 2 sulfurs and 4 oxygens. Let me just double check and make sure that that's correct. 32.06 times 2 plus the 12 times 4. Oh, sorry, that should be 112. I added an extra one. Hi, Gabby. My daughter. You want to say hi? You shy? Okay, I've got to work now, so please go bother Daddy. I don't know where daddy is either. I told him, I was like, dude, I have 3 hours of lecture I have to do on Tuesday. Just make sure the kids are ready and that you've got them occupied with an activity. And like 10 minutes before lecture, he's sitting in front of the TV, like watching the Tour de France. I'm like, go take the kids somewhere. Oh. I kind of like to give him a hard time, but he's awesome. He is an awesome dude. So we're going to keep him for now. 16 times 4, that's 32. Why am I having so much? 32.06 times 2 plus 16 times 4. No, I was right the first time. It's 128. James, can you give me confirmation on that? You're the only face I can see. Yeah, 128. I'm second guessing myself. Yeah, Andrea, so you take the mass of 2 sulfurs, which is 32.06. You multiply it by 2 because there's 2 of them. We take the mass of oxygen, which is 16. We multiply it by 4. We get those 2 values and we add them up for a total of 128.12 grams per mole. So start with our, oh, good. Okay, good. So start with our 12.7 grams of the disulfur tetraoxide. And again, as you guys get better at these problems, you won't necessarily need to set it up like so anal retentively where you do the flow chart for every single thing. But in the beginning, it might be helpful for y'all. So first step, go from grams to moles of the compound. So we're going to put the mole on the top. So 1 mole of S2O4 is going to yield 128.12 grams of the S2O4. The grams will cancel. I'm going to keep just chaining them together. So the next step is to go from moles of the compound, which I want to put on the bottom this time because I want that to go away. How many moles of sulfur do I get? 2 moles of sulfur. 2 moles of the sulfur, right? So the moles of the compound go away. Now we're in moles of the sulfur, the moles of the element that we're looking for, and we want to get it into grams. Well, let's put the mole of the sulfur on the bottom and let's put the gram on top, which is 32.06. So moles will cancel and we'll be left with grams of the sulfur. So again, when I'm doing these problems, I don't think about it as, oh, if I'm going from this direction to this direction, I need to multiply or divide. I set it up in the dimensional analysis where everything cancels so that at the very end, I get the units I want and everything else was removed. So we're going to take that 12.7, we're going to multiply it across anything on the top that isn't a 1 value. So we've got the 2 and we've got the 32.06, right? And then we have to divide it by anything that's on the bottom that isn't a 1. So we've got that 128. So take that 128.12, and I end up with a value of, with 3 sig figs, 6.36 grams of sulfur. And you can ask yourself, like, does this conceptually make sense? So if I've got 12.7 grams of the compound, if 6.36 grams are sulfur, does that work? Yeah, we wouldn't want that number to be bigger than the total compound amount. And we wouldn't want it to be some like obscure decimal. We wouldn't want it to be 0.0052. That would be too small. So this feels like something that's sort of, right, you know, it's like about half. It makes sense to me. Okay. So I'm going to have you guys work on one of these problems on your own. Same setup, different compounds, and I'll give you all about 5 minutes for it because I'm going to have you do a little nomenclature with it as well. So how many grams? How many grams of, what do I want to do? Nitrogen are in 85.73 grams of, let's see, what do I want to do here? Calcium nitrate. All right, so how many grams of nitrogen are in 85.73 grams of calcium nitrate? Very similar to the last problem. You got to do the work though. So I'll see you guys back 5 minutes from now.
don't ever ask her questions in class. Like, how do you figure something out? Because as long as I can.
Hello? Is somebody there? Someone's got their mute off. John, I think it might, I don't know. Okay, somebody was. I don't know if you had a specific question for me. All right, just another minute. All right, so how many grams of nitrogen are in 85.73 grams of calcium nitrate? So given information is that we have 85.73 grams of this thing called calcium nitrate. Well, what is calcium nitrate? Calcium, Ca with a 2+, it's a metal, nitrate, NO3 with a -1 charge, it's a polyatomic ion, flip-flop. So we're gonna have Ca parentheses NO3 2. If you can't get that right, it throws off your ratio, right? And then it throws off the whole calculation. And that nomenclature, man, it just kind of keeps coming back around. So the sooner you can get that nomenclature tacked down, the better off you're going to be. We're trying to find grams of nitrogen. So quick flow chart, we're going grams of calcium nitrate into moles of calcium nitrate into moles of nitrogen into grams of nitrogen. So 85.73 grams of the calcium nitrate, CaNO3 2. What is the molar mass of calcium nitrate? It's 164. So 1 mole of our calcium nitrate will weigh 164.088 grams of the CaNO3 2.
Mom,
hold on 1 second. Sorry, we're here with another family and there's just so many kids coming. I did something. Where did you get 164? Where did I get 164? Well, I got 164 off the internet by typing in molar mass of calcium nitrate. But how do you calculate it? I can show you that. So we'll take the mass of calcium. And again, I don't have a periodic chart. Yeah, so let me pull one up. Periodic table, where are you? All right. That one doesn't even have the molar masses on it. Okay, so we've got a calcium. Move that over a little bit. Which is 40.078, and there's one of them. Nitrogen, we can round that to 14. So nitrogen, we've got a molar mass of 14, and we have a total of 2 of those. All right, and then oxygen has a molar mass of 16, and we have 6 of those. So, you know what, we get 40, we get 28, get 16 times 6 is 96. Let me just make sure the internet is right. Yeah, 164 grams per mole. There's an extra decimal or 2 in there, which, you know, is probably coming from this calcium mass. Does that make sense where that number came from? Put in the wrong element. Okay, Rachel, yeah. So yeah, you wanted those, you know, those little pesky details will come back and bite you, because it's like, oh, if I, instead of using the calcium mass, I happen to use, you know, the mass right next to it, it'll throw that number off, and then it'll throw all your calculations off. So back to here. So now we know where that came from. Now the relationship between the moles of your compound and the moles of what we're trying to find here is 1 mole of the compound, right? 1 mole of this calcium nitrate is going to yield how many moles of nitrogen? We'll look at the compound. 1 of these is going to give us 2 of those. All right, so 2 moles of nitrogen for every 1 mole of this thing. Then the last step is just to use the molar mass of nitrogen, which is approximately 14. So 1 mole of nitrogen give us 14 grams of nitrogen. And look at that, bam, there goes the grams of the compound, there goes the moles of the compound, there goes the moles of the element, and we'll be left with just grams. So then we just simply plug it into the calculator, 85.73 times 2 times that 14. And then we need to take that whole thing and divide it by the molar mass of the compound, which is what, 164. 164 is close enough. 3 sig figs here. So I'm going to round this to 14.64 grams of nitrogen. James is looking at me like that doesn't make sense. So let me just double check. 85.73 times the 2 times the 14 divided by 164. Yeah, 14.64. 1121, which makes sense. It's under the 85.73, which is the total compound amount. It's not eating a majority of it. It's eating some sort of minority of it, but it's not like an obscenely small number. So I like it. Yeah, I'm getting the same thing. Anyone else having issues with this number? They feel good with it pairing up? Good. Brittany says she's good. She's getting consistent stuff. Okay, perfect. So again, it doesn't really matter, you know, what the compound is or what the individual thing I'm asking for is. You always follow this system. So it probably will be useful for you on your next test to have this sort of master chart here. And then you can do all sorts of things. You actually can do like things like this. Hey, what if I gave you the number of molecules of a compound and I wanted you to find grams? You could do that as well. You could go molecules to moles, moles to moles, and then moles to grams, right? Or you could go molecules to atoms, atoms to moles, moles to grams, right? So there's all sorts of different ways to flow through this. So keep this handy. You guys feel okay with this grams to moles to grams thing? Or do you want to do another one? Or I don't want to, like, James is like, I'm good. I got it. One more. Okay, we'll do one more, but I'm gonna challenge you guys. I'm gonna give you just about 3 minutes to work through it. So let's say, and I'm gonna ditch the nomenclature part. I'm just gonna give you everything so that we can keep it fast. Got confused on the last 2 steps. Okay, well, let's do one more and then we'll work through it. So how many grams of oxygen are in 185 grams of magnesium hydroxide, MgOH2. Okay, so 3 minutes for this, and we'll go over it. All right, so for this problem, we're going to go from grams of MgOH2 into moles of MgOH2 into moles of oxygen, and then moles of oxygen into grams of oxygen. So we're given that we have 185 grams of MgOH2, and we want to find grams of oxygen. So with this flow chart here, because it looks like someone was asking, they said they got confused on the last two. So here we need the molar mass of MgOH2. So magnesium hydroxide, what is your molar mass? MgOH2, molar mass, 58.32 grams per mole. Where did that come from? It's the mass of a magnesium, 2 oxygens, and 2 hydrogens. This middle step, how do we go from moles of the compound into moles of the individual material? Well, we have to look at the subscripts. So one compound, one little packet of this, contains how many oxygens? 2 oxygens, 2 hydrogens, and 2 oxygens. So the ratio between these things is one compound, or 1 mole of the compound, yields 2 moles of the oxygen. That's the 1:2 ratio. The last thing here, we need the molar mass of oxygen. Where do we get that? That's just off the periodic chart. It's 16 grams of oxygen for every 1 mole of oxygen. So now we just stick it in. We got 185 grams of MgOH2. We want to convert that into moles. 1 mole of MgOH2 weighs what we got here, right? That 58.33 grams, specifically of the MgOH2. That gets us from here to here. The next thing is we want to go from moles of the compound into moles of oxygen. So I'm going to put the moles of the compound on the bottom, 1 mole of the compound, MgOH2, and you always give the 1 value to the compound. Just assume you have 1 of them. We will then have 2 moles of the oxygen, because 2 oxygens come from every 1 of these. The last step is to go, so let me add oxygen there, yeah. 1 mole of oxygen, we're going to use this value here, gives us 16 grams of oxygen. That is the molar mass of the oxygen. So compound goes away. Moles of compound go away, moles of oxygen go away, and we're left with grams. Hopefully this is starting to feel kind of repetitive. So we'll multiply by, we'll take our first value, multiply it by 2, multiply it by 16, and then we're going to divide that by 58.33, and I get 101 grams of oxygen. If you rounded, depending on how many numbers you used, you may have gotten 102. Okay, close enough. You're close enough. This is where sig figs start to matter like a little bit less. I'm not going to give you one problem that's 101 and or one answer is 101 and one answer is 102 grams. And I'm like, you know, tricky. You've done all this work and it's going to come down to that. That's not going to be the case. Okay, the numbers will be distinct enough. Is it 58.32 or 58.33? It depends, Andrea, on the periodic chart you're looking at. Either of those are going to be okay. Yeah, you'd be fine with either of them. I understand how to write it all out and find the numbers, but I keep getting confused on rounding the masses of elements and then getting different numbers. Don't round the mass of the elements. Use as many decimals as you can, Rachel. So if you're having trouble with that, don't round them. Just use all the decimals.
Write out like the whole mass number off the periodic chart.
Yes.
Around it.
Use more. Yes. I mean, look, for oxygen, do you see how oxygen's like 15.9994? That's close enough to 16 to just use it as 16. But look at chlorine. Chlorine's like 35.45. That we definitely don't want to round that. We want to use those decimals.
So you just use the whole 35.4527 or the 35.45.
I would use at least two decimals.
Okay.
Okay, yeah, at least 2 decimals. If you can have the patience to use more, use more. You'll see me start to get lazier as the semester goes on. But try and use 2 decimals if you can. Okay, so this is actually super helpful here because we're gonna come back to this whole idea a little bit later. So if you kind of understand this grams to moles to grams thing, this will lead us through chapter 8 as well. So let's go back to the slides. The slides have their example problem on how to do this. They're doing it with sodium because remember we were talking about like how much sodium do you need if you have a certain amount of sodium chloride. They did a problem where, what's the mass of the sodium in 15 grams of sodium chloride? Hopefully that problem doesn't sound so scary anymore. You've got grams of sodium chloride. You want grams of just the sodium, grams to moles to grams. You use the molar masses, the mole ratio, and you just send it through. All right, and in this case, it's 5.9 grams of sodium for every 15 grams of sodium chloride. If you want to, you can go ahead and hold on one second. Okay, sorry guys. So mole relationships in a chemical formula, we've already talked about this, but this idea that like, hey, you've got CCl4. That's one carbon in the center and 4 chlorines on the sides. It's a ratio of 1 of these will yield 4 of the chlorines, right? It's like the spider leg thing. You get 8 legs for every 1 spider, 4 legs for every 1 chair. So it's a mole to mole ratio. Okay, so let's move on to another thing. I think this is actually going to be much easier than what we did just prior to this. So mass percent, or the mass percent composition, this is the formula. All right, so mass percent of an element within a given compound follows this formula. The mass percent of X, being whatever that individual thing is, equals the mass of X in the sample divided by the mass of the compound times 100. What is a percentage? Right, it's the part divided by the whole times 100. We have the part or the element we're looking at divided by the whole, and then we multiply it by 100. So think of it like, hey, 3 out of 10 students got A's on the test. What percentage of students got A's? Well, you take the 3, you divide it by 10, and you multiply it by 100, you get 30%. We're doing the same thing, but we're doing it with the masses. Now, where do these mass values come from? You can collect them experimentally. So you may see some problems where they're like, hey, the mass of the element is this and the mass of the compound is this. Divide them by each other and multiply by 100. Or you can do it in a theoretical way where you just, in theory, in an idealized situation, you would use the values off the periodic chart. So let's look at, this is one using a experimental value. So it says, a 0.358 gram sample of chromium, so that's just the chromium, reacts with oxygen to form 0.523 grams of a metal oxide. And metal, when they say metal oxide, that's the compound. Okay, so we know how much chromium we have, and we know how much the whole material is at the end. So mass percent of chromium, which looking here, mass percent of element X, in this case, we're looking at chromium, you take the mass of the chromium and you divide it by the mass of the compound or the total thing and multiply it by 100. So how much of this total sample is chromium? You take the part, you divide it by the whole, and you multiply it by 100, or in this case, you get 68.53%. Not too challenging. I'm not going to teach you guys this is a conversion factor thing. I think that doesn't work and it's confusing. So we're just going to bypass all that. So you can figure out the mass percent composition from a chemical formula. Let's say we've got this thing here. I think this is like a type of chlorofluorocarbon. So we've got CCl2F2. And we want to figure out what's the mass percent of just the chlorine in this hypothetical material. It doesn't give us any experimental value, but we do know the formula. So the mass percent of chlorine is going to equal 2 of the chlorine masses, right? Because you do get 2 of them. You got to take into account both of them, divided by the molar mass of the whole clump, right? The parts divided by the whole to give us 100. Or times 100 to give us the percent. Where do these numbers come from? Take them off the periodic chart. So the mass of 2 chlorines is 35.45, multiplied by 2. And then the mass of this compound, well, you calculate it. You take a carbon, 2 chlorines, and 2 fluorines, and you add them together. They do the same thing for this one. This is Freon. This looks similar to the last one, but it's not quite the same. This has 2 carbons, 4 chlorines, and 2 fluorines. What's the mass percent of the chlorine? Well, I need to take 4 chlorines and divide it by the mass of the whole thing, right? So 4 chlorines divided by the molar mass of the total to give me 100, or times 100 to give me the percent. So 141.8 grams is that 35.45 times 4, and the whole mass of this is 203.8 times 100. It's really not that hard. So let's do a couple of these. We'll do one together and then I'll have you guys do one. So we're going to clear all this out. What is the mass percent of oxygen in calcium phosphate? So mass percent of oxygen is going to equal the mass of the oxygens, however many that is, divided by the mass of calcium phosphate. Times 100. So we need to know what calcium phosphate is. That is calcium, Ca has a 2+ charge. Phosphate is this thing, PO4 with a 3- charge. It's a polyatomic ion. Remember the ATEs, polyatomic ions? You would reference your polyatomic ion sheet. I just have these memorized because I've done these things for so long. So don't be intimidated if you're like, how can she pull this stuff out of thin air? It's like burned into my brain. So we're going to flip-flop. Calcium gets the 3. Phosphate, PO4, gets, oh, come on, pen, don't fail me now, gets the 2. If you can't do that, everything else, again, sort of falls apart because it's all based on these ratios. So what is the mass of calcium phosphate? That I am definitely not going to calculate. I'm going to just look it up online. So calcium phosphate mass. You can think, oh my gosh, my lazy chem teacher, totally lazy. You would take the mass of 3 calciums, the mass of 2 phosphates or phosphoruses, and 8 oxygens for a total of 310.18 grams per mole. So that's the bottom value, right? What's our top value? It's mass of oxygen, but how many oxygens do we have? We don't just have 1. We actually have 8 oxygens. So I need to multiply by that value by 8. So the mass of oxygen, I'm going to write it down here, is 16 times 8 all over 310.18. What are the units on these? Both of them are grams per mole. So you can kind of just, they disappear because percentage doesn't have a value like that. We're going to multiply it by 100. 16 times the 8 gives us 128, and we're going to divide that by the big mass of the whole compound. And then multiply it by 100 or move the decimal over 2 places, and you should get 41. Let's see, how many sig figs do we want with this? I guess since we're using values, I'll give it 1 decimal. Again, I don't care too much. 41.3%. So 41.3% of calcium phosphate by mass is coming from the oxygen. So just under half is, and there's, I mean, that makes sense. There's a lot of oxygens, right? There's 8 oxygens in there. They're light elements, but there's 8 of them. That's not too bad. I feel like that's kind of easy. It's like refreshing. Let's have you guys do one. So what is, I'm like trying to be creative here, but I feel like I don't need to be creative here. What is nitrogen's? Use an element we haven't used in a while, but what is nitrogen's mass percent in, I'll just give you the formula, aluminum nitrate, AlNO3, 3. You know, and I don't want just the mass percent of nitrogen. I want the mass percent of, what is nitrogen's mass percent? I also want aluminum and I want oxygen. Okay, I want you to do the mass percent for all 3. Hint, they should all total 100%. Okay, if we're finding each one, they should add up to 100%. So I'll give you guys, I'll give you 4 minutes for that one since I'm having you do the other 2. Okay, so we're gonna figure out the mass percent for each of these. So mass percent of nitrogen is going to equal, let me put mass, not just percent, but mass percent of nitrogen is going to equal the mass of nitrogen times how many? Times 3, because we've got 3 of them within this, and then divided by the compound's mass. And the compound mass is 212.996 times 100. What is the mass of nitrogen? It's like approximately 14. Okay, so now that I've given my secret away about how you can plug into Dr. Google, hey, what's the molar mass of aluminum nitrate? You know, use that, but also you definitely want to be able to calculate these, especially if you're going to go back and do 151, at least understand the concept of how to do it and know, okay, if I have to do it, I can do it. But yeah, I use that quite often. So 14 times 3 of them, because you got to take into account that there's 3. If there were 2, you'd multiply by 2. And then we're going to divide it by that 212.996. If you rounded that to 213, that's okay as well. Multiplied by 100. I'm going to do just one decimal place here. So 19.7%. Now we're going to do the same thing for aluminum. So mass percent of aluminum is going to equal the aluminum's mass, which is 26.989, divided by the same mass, because we're talking about the same compound. So we get to repeat that, 996. You get to use that a couple times, times 100. So we get our 26.989 divided by 212.996 times 100. And that is roughly 12.7%. The last one better make up a good chunk, right? Because I've got a lot of percentage left. I need to get to 100. One way you could solve for this last one is to take 100 and subtract those two, right? But let's make sure we're doing it correctly and make sure they add up to 100. So I'm going to take the mass of oxygen, which is 16, and I'm going to multiply it by how many oxygens? 9. 3 times 3 gives us 9. Lots of oxygens in there. Divided by that 996. So 16 times the. All right, looking good. It looks like it's a pretty big chunk, 144 for that top value, divided by the 212.996. Okay, oh, we want to multiply it by 100 too. And I get 67.6%. All right, let's go through and check and make sure we get, it doesn't have to be exact, but let's get close to 100%, right? So we'll take that 67.6, let's add it to the 12.7 and add it to the 19.7. And I got exactly 100. Okay, so I guess I did a really good job there. Nice job, Candace. That's like easy. It's like super easy. Questions on this? You see mass percent? I mean, it's like a giveaway almost. So if you see mass percent on the homework, just go to this system. Don't use any of that weird, the mole stuff, the converting between grams, Avogadro's number. Don't use that. Just do this system here. So we have been able to, and let me add the mass percent of oxygen. We've been able to go from a formula and figure out the mass percent. Right? That's pretty cool. Can we go the other direction? Can we have the mass percents and figure out the formula? We can. It's more work that way though, okay? It's a little more work to go backwards, and there's a specific set of steps that you need to follow, and I'll show you guys. So you should be good going this way. Let's start going into moving backwards. So what if I gave you certain mass percents, like even this right here? I could say, hey, it's 19.7% nitrogen, it's 12.7% oxygen, and it's 67.6%, or 12.7% aluminum, and 67.6% oxygen. What is the formula? So we'll look at water, because we know the formula for water. We'll come back to molecular formula and empirical formula in a minute. So calculating the empirical formula, and remember, what is empirical formula? That's the lowest ratio number, right? Molecular formula is a multiplier of it. The empirical formula, I guess maybe we should go over that real quick. So an empirical formula for hydrogen peroxide would be HO. The molecular formula, what's actually happening is H2O2, the empirical formula, lowest ratio. So you take the molecular and divide it by some solid whole number to get the empirical. So in order to calculate the empirical formula of, let's say, water, we know the formula, but we're going to prove it. So we're going to decompose a sample of water in the lab. And what happens is we produce 3 grams of hydrogen and 24 grams of oxygen. Determine the empirical formula for water. We know it's H2O, but let's prove it from these values. So the system that you're going to follow is this. You write down or calculate as given all of the masses of each element present. If instead of giving it to you as a mass, our problem here with the water gives it to us as grams and gram mass, right? But if the problem had given it to you as a percentage, just assume that you have a 100-gram sample and take the percentage off and put it as a gram. Okay, so if we were looking at, like, for instance, this here, let's say I gave you these values and it was 19.7%, 12.7%, and 67.6%. The first thing you would do is just ditch the percentage and put it as a gram. You can do that for this specific type of problem because we assume a 100-gram sample. So those would all be 100-gram values. It gives us the same ratio. So we have our values for water right now. What did we say? It was, kind of do this together while we're going over these steps. We have 3 grams of water and 24 grams of oxygen. So go ahead and write that down. 3 grams of water. I'm going to make it 3.0. So we have a sig fig, 3.0 grams, sorry, 3.0 grams of hydrogen. Already forgotten. 24 grams of oxygen. Again, if it was a percentage, put it as grams. So what do we do for the next step? Well, convert each mass from step 1 into moles using the specific molar mass for the element. Why do we have to do that? Well, remember, what is a chemical formula? A chemical formula is a molar relationship, right? It's moles of one thing in relationship to moles of another thing. It's not a mass relationship. So I need to get out of mass and get it into moles. So let's convert both of these values into their corresponding moles. So we use the molar mass, right? 1 mole of hydrogen always weighs like 1.01 grams of hydrogen. Oxygen, 1 mole of oxygen always is 16 grams of oxygen. We're just using the molar masses for each given element. So this one here works itself out to approximately, this is going to be an approximate thing. If you're within like a 1/10, you can just round it. So this is 3. Let's say this is 3 moles of hydrogen. And then 24 divided by 16 gives us what, 1.5, I think? Yeah, gives us 1.5 moles of oxygen. So now I have a mole relationship. Right here was a mass relationship. It was 3 grams of hydrogen for every 24 grams of oxygen. Now I have them in moles, 3 moles of hydrogen for every 1.5 moles of oxygen. This is the molar relationship. What's wrong with it? And it's not that it's not a wrong ratio. It's just, it's not in whole numbers. And we like things to be in whole numbers when we have a chemical formula. So I'm going to actually put this into, I think the next step says, write it as a, write down a pseudo formula for the compound where the moles of each element are the subscript. So I'm going to write a compound where these are the subscripts. So I've got hydrogen and it's going to have a 3 as its subscript. And then I'm going to have oxygen and it's going to have 1.5 as its subscript. Again, this ratio, it isn't wrong, it's just not whole number. We want it to be a whole number because we like whole atoms. So what's the fastest way to get this thing into whole numbers? Find the smallest decimal and divide everything by that decimal. So what's the smallest decimal we have here? 1.5, right? So I'm going to divide everything by that 1.5. This is just the simplest way to get to whole numbers. What is 3 divided by 1.5? Plug it in your calculator, you should get 2. What is anything divided by itself? 1. Oh my gosh, we came up with water, H2O, right? So we were able to take the experimental values and get the correct formula. Obviously, we knew the formula for water was H2O, but you don't always know the formula. So this was just a way to sort of prove it. So we'll do one where we don't know what the formula is. We don't know what the end answer is. So you first write out everything as a gram. If it's a percentage, write it as a gram. Convert it to moles, hope you get whole numbers. If you don't get whole numbers, divide by the smallest decimal and hope you get whole numbers. Okay. If you don't get whole numbers after that, like let's say we still had a decimal hanging around, we can do one final thing here. If the subscripts are still not whole numbers, multiply by a subscript to get to a whole number. So here are the values. Like if you had a remainder of a 10 or a 0.10, you'd multiply it by 10. If you had a remainder of like 0.5, you'd multiply it by 2. And you multiply everything by that value. So let's do a couple of these. I have some on, these ones are hard for me to make up. So I'm just going to use the reference sheet that I have in the notes. Don't forget to take your second test. See, 5 of you have taken your second test. Okay. I want to see more than 5 sometime tomorrow morning. But you have until midnight. Where are we? We are moving and grooving, man. We are like over halfway through the semester at this point. Once you've taken your second test, you'll be pretty much halfway through. Okay, so let's look at this first. I don't like the, I like the other. I have another sheet I like better than that one. I think it's this guy here. Yeah, this guy's good. Okay, so we're gonna do, we'll do 1 together and then I'll have you guys do 3 on your own. So number 1, what is the empirical formula of a molecule that contains 65.5% carbon, 5.5% hydrogen, and 29% oxygen? So let's write all those out. We've got 65.5%. 65.5% carbon, 5.5% hydrogen, and 29% oxygen. So they didn't give us grams here. They gave us percentage. That is okay. We just assume 100-gram sample, because if we had a 100-gram sample, these would all be gram values. So I'm going to go ahead and right off the bat, get rid of my percentages and just write it as a gram. Now, one thing that students sometimes will do is they'll start writing these as their subscripts and then divide from there. We can't do that, right? Because this is a mass relationship. We need to get it into moles. First step, go into moles. So I need to convert carbon into moles. 1 mole of carbon is 12.01 grams of carbon. Need to get hydrogen into moles as well. So 1 mole of hydrogen is 1.01 grams of hydrogen. And then 1 mole of oxygen is 16 grams of oxygen. So let's run those through your calculator. While I'm doing it, compare answers here. So 65.5 divided by 12.01 gives us 5. Somebody's got their, who is that? When backing up in their car? It sounds good. Okay, 5.45 moles of carbon. Let's do hydrogen, 5.5 divided by 1.01. Ooh, I like this, 5.45 moles of hydrogen. Why do I like that? Because those are like similar ratios, right? You know, if I like divide those, it's gonna be good. And then we've got this 29 divided by 16. And that thing is like totally out there, 1.8125 moles of oxygen. So after this step, now we know the mole ratio. This is a correct mole ratio, but we want whole numbers. So let's write a pseudo formula. Carbon's going to get this, the 5.45. Hydrogen's going to get this, 5.45. And oxygen's going to get this thing, 1.8125. What did we say we did first to get these whole numbers? Divide by the smallest decimal. Don't divide by the biggest one. Why? Because that's just the rules. That is the system that works most efficiently. There are other ways to figure this out, but this just is the easiest. So we're going to divide by that 1.8125. Everything. So 5.45 divided by that 1.8125 gives us 3.00689. That is like totally close enough to 3. Okay, so carbon gets a 3. Hydrogen, well, that's the same number. It's also going to get a 3. What is oxygen going to get? Well, divide this by itself is 1. And we came up, awesome, with a chemical formula from these values. So grams into moles, divide by the smallest number. Hope you get whole numbers. If you don't get whole numbers here, you have to multiply, and we will do maybe an example of that a little later. You guys want to try one on your own? Let's try one on your own, so make sure you've got the skills. So I want you to do number 3, skip 2, that corresponds with 1. We'll come back to that. So number 3 says, what's the empirical formula for a molecule containing 18.7% lithium? All right, so you got 18.7% Li. You've got 16.3% carbon or 16.3% C and 65.0% oxygen or O. So 3 things given to you in a percentage. I'll give you 5 minutes for this one because these can take a little bit of time. All right, so let's look at this problem with lithium, carbon, and oxygen. Okay, so we know that we have 18.7% lithium. We've got 16.3% carbon, and we have 65.0% of the remaining oxygen. Where would these values come from? It would be something that you would calculate experimentally, like in the lab, which obviously you guys aren't going to be doing. So this information would be given to you. Okay, so you're not going to have to like come up with these numbers. So since it's a percentage, again, assume 100-gram sample. Let's just strip that percentage away. That's probably the easiest step, and just switch it over to grams. Now, mass relationship, we got to get it in a mole relationship. So each one of these, I'm going to convert using their molar mass. So 1 mole of lithium, what are you, like 16? Or I mean, rather 6.9. Some of them I have memorized. Some of lithium I don't use quite as much as the other guys. Mm-hmm. 16.94. Okay, 6.94 grams of lithium. Moles of lithium. Carbon, 1 mole of carbon, 12.01 grams of carbon. And then 1 mole of oxygen, 16 grams of oxygen. So what do we have? 18.7 divided by that 6.94. And we get kind of a funky decimal of 2.69. We're going to just go with that though, because, you know, when we divide out, hopefully it takes care of itself. So 16.3 divided by that 12.01. We also get a weird sort of 1.357 number. It's kind of like half of this though, so I'm liking that. Moles of carbon. And then this last one, what, 65 divided by our 16, we get 4.0625 moles of oxygen. We got all sorts of different numbers, right? It's kind of a mess right now. So let's write it in our pseudo formula. Some people don't write it in the pseudo formula. They'll just divide it out here and then write the formula later. That's fine as well. So I'm going to put lithium with that subscript now of 2.69. We've got our carbon, which is 1.357. And then we've got oxygen at that 4.0625. Let's see, we got a comment here. You rounded up lithium to 7. Yeah, Brittany, don't round up lithium to 7. Try and keep at least 2 decimals. I mean, it probably isn't the end of the world. You'll probably still be able to get the same one, but I would keep it. Okay, so we're going to divide by the smallest number. So the smallest of the decimals here is that carbon one, the 1.357. So everything's going to get divided by 1.357. So what is 2.69 divided by that 1.357? Come on, whole number. Come on, whole number. Okay, 1.98. That is totally close enough to 2 to be rounded to 2. So we're going to keep that as lithium with a 2. Anything divided by itself is 1, right? So carbon gets a subscript of 1. And then for that 4.0625 divided by 1.357, come on, whole number. Oh, we get 2.99. That is totally close enough to 3 to keep it as 3. What did we get here? Does anyone know what the name of this thing is? Lithium carbonate. Lithium carbonate. Cool. Able to figure that out. So I like this system. I think, you know, it's really applicable. We use it a lot when we're doing experimental stuff to try and figure out identify what something is, what its compound is. Everything you've calculated thus far, though, has been an empirical formula, meaning it's the lowest ratio, right? So 2 lithiums to 1 carbon to 3 oxygen. We can't get this any lower. as in its molecular ratio value than this. But we are going to calculate molecular formulas. So molecular formulas are some multiplier of your empirical formula. So again, if we go back here, I sort of skipped over this part. A molecular formula is always going to be equal to your empirical formula, your lowest ratio formula, times a value n. And n has to be a whole number. So like the molecular formula is 2 times as big, or it's 3 times as big. It's not going to be 1.8 times as big. It's always going to be some sort of whole number. So when looking at the empirical formula for hydrogen peroxide, which is HO, the molecular formula is H2O2, right? How do we get from here to here? We multiply by 2, or the n value is equal to 2, twice as big, right? So the real life situation is twice as heavy as the lowest ratio. So how do we come up with, let's skip over that. How do we come up with the value n? N is always going to equal this. N equals molar mass. And I don't really like how they say this. I want to say molar mass of molecular formula. So put molecular formula, molar mass on top, and then put empirical formula, molar mass on bottom. Remember, the molecular formula is a multiplier, so it's the heavier thing. The empirical formula is the lighter thing. So the heavier thing divided by the lighter thing. How much heavier is it? Is it twice as heavy? Your n value will be 2. If it's 3 times as heavy, your n value will be 3. This top number, give yourself a little note that says this top number is always going to be given to you. Or if you were doing an experiment, you get calculated experimentally, but we're not doing experiments this semester. So this will always be given to you. So on a test, know that that top number should be somewhere in the problem. The bottom number, the empirical formula, you may have to calculate this. Like you may have already calculated the empirical formula from a previous problem, and now you have to calculate the molar mass for it. So this, I'm going to say calculate. Once you're able to figure out your n value, that tells you how much bigger this is than this. Then if you know this, you can find this, right? Because you know how much bigger this has to be. Or you take your empirical formula, in this case, they're using CH2O, and you multiply it by an n value. So let's do it. I feel like this is one of those things we kind of got to do to understand. So we'll go back to that problem we were looking at. Get out of here. This problem we were looking at earlier. So this empirical formula for the carbon, hydrogen, oxygen mix, we said, oh, I don't even remember. What was it? I think I deleted it. James, was it C3H3O? Yeah, okay. So this is the empirical formula. How do I know it's the empirical formula? Well, can you get a lower ratio than 3, 3, and 1? No, there's no way to divide that out. And that whole process that we did, where we converted to moles divided by the smallest number, that always pops out the empirical formula. That isn't giving you the molecular formula. So in this second problem, it says, hey, if the molar mass of the compound is actually 110 grams per mole, what is the molecular formula? So anytime it gives you molar mass like this, it's talking about the molecular molar mass, like what's actually happening in real space. So molecular formula, which is what we're looking for, molecular formula, is going to equal my empirical formula, this thing here. So this C3H3O times some value of n. Okay, we need to figure out n. So remember, n equals molecular mass over the empirical mass. Here, I swear I can spell. Actually, I can't swear that I can spell. I'm not a very good speller. Empirical mass. Okay. Molecular mass, I said, is always given to you, right? So let's see if we can sniff it out in that problem. Right here, 110 grams. Okay, so that's talking about the molecule as a whole. So let's just plug that in. right away. So this thing is going to equal that 110 grams per mole over, well, what's the empirical mass? This you have to calculate. How do you calculate it? Well, don't you know the empirical formula up here? So we just figure out its mass. Let's take 3 carbons, add it to 3 hydrogens, and add it to 1 oxygen. So 12.01 times 3 plus the hydrogens, 3.03, plus oxygen, which is 16, we get roughly 55. Okay, so the mass on this guy is 55 grams per mole. So I'm going to put that as the bottom value, 55 grams per mole. Remember, this thing is given in the problem. This thing is sometimes given, sometimes you have to calculate it. Well, what is our N value? 110 divided by 55 is 2. So what that is saying is that your molecular mass is twice as big as your empirical mass, or your molecular formula is twice as big as your empirical formula. So we're not done just yet. We have to take that 2 and thread it back into that formula. So we take the C3H3O and multiply it by 2. Now, when I multiply it by 2, I multiply every subscript by 2. So the molecular formula is now going to be C6H6O2. This thing is twice as big as this thing. It's twice as heavy, 2 times. Any questions on that outside of like, we're going to do another 1 or 2 of them, but questions on what we're calculating here and how empirical and molecular relate to each other. Molecular is some multiplier of your empirical. You have to find that multiplier by comparing the masses. How much bigger is the one guy from the other? So I want you to do this with problem 3 that we worked on, that lithium carbonate and oxygen. It says, hey, if the molar mass of the compound is 73.8 grams per mole, what is the molecular formula? Remember, we said that this was lithium carbonate, so the formula is Li2CO3. Now you know what the molar mass of the molecular is. So follow the same system that we just did, that you can tell me what the molecular formula is. And I will give you guys, I'll give you guys about 5 minutes for it. If it seems, if you're doing the problem and you're like, am I doing this right? I calculated a number and I think I'm doing it right. You've done it right. It's a little, this one's a little weird, slightly weird. So give it a try. Try it out through that system. Just another 30 seconds and then we'll come around. 73.8. This guy. All right, so I don't know why I wrote that there. So our empirical formula for this one is Li2CO3. We had that the molecular formula's mass is 73.8 grams per mole, right? So if we want to find the molecular formula, that is going to equal the empirical formula, right? Li2CO3 times, I don't know why I put 2, times N. So what is N? N is going to equal molecular mass over the empirical mass. Molecular mass is given, 73.89 grams per mole. Empirical mass you calculate, right? So you have to take this thing's mass. Well, what's its mass? I think it's 73.89, isn't it? It's the same thing. So what is our N value here? 1. You guys get 1 for your N value? So what do you plug in here? 1. So what is your molecular formula? It's the same thing. Li2CO3. Sometimes that happens. Sometimes, especially with like salts, where you have a metal and a non-metal, the molecular and the empirical formula are actually the same. So that's why I was saying if it was like tricking you out and you're like, why is it 1? What's 1? It just means that your molecular formula and your empirical formula are the same thing. So I'm going to give you guys one more of these to work through, and then that will be it for the week. That will be all of chapter 6. Chapter 6 got a lot of stuff. It's kind of hardy. I want to get a good one though for this. So let's say we're going to do the whole thing. You're going to give me the empirical formula and then you're going to calculate the molecular formula. Okay, so let's calculate the empirical formula. Of a compound. That contains 43.7% phosphorus. Yeah, that's the important part. 43.7% phosphorus, and the remaining 56.3% is oxygen. by mass. And then I also want you to say, to do this. So this is like, let's say this is part A. Part B is calculate the molecular formula if the actual molar mass is, hold on one second. I got to come up with this part. Start with the first part. I'll write this in just a second. So yeah, start with A. Okay, so real quick, the second part, it says calculate the molecular formula if the actual molar mass is, it's really big, 425.7 grams per mole. 425.7 grams per mole. Okay, so do A and do B. We will meet back in 7 minutes, go over all that, and then we'll be done for today. We'll do another minute here and then we'll go over it. All right, so let's get through this last problem here. So calculate the empirical formula of a compound that contains 43.7% phosphorus and 56.3% oxygen. So 43.7% phosphorus, let's just go with grams, right? Because we know we can go percentage to grams. And then we've got 56.3 grams of oxygen. So we're going to convert these. 1 mole of phosphorus is going to be roughly 31 grams. And then 1 mole of oxygen, 16 grams. And so we end up getting 1.41 and roughly 3.52 moles of phosphorus and moles of oxygen. So let's put that into a pseudo formula and say phosphorus has 1.41, oxygen has 3.52. Divide those by the smallest. So we'll divide it by that 1.41. Phosphorus gets a value of 1, oxygen gets a value of 2.5. I wanted to do a problem like this where we ended up with a decimal. Ugh. So we're not quite a whole number. So what do we have to do? Well, you reference that chart that's over here. And what is our decimal? What's the decimal that's giving us trouble? Right? The decimal that's giving us trouble is that 0.5. So what do we do when we have a 0.5? We multiply everything by 2. Okay? And that may have a cascading effect on how you were able to answer the rest of it. So let's multiply everything by 2. And that's why I wanted to go over one more just so that we are good here. So we multiply this by 2. That goes to this and it goes to this. So phosphorus now becomes 2. And what does oxygen become? 5. 2 and 5. You guys good with that on what happens if we end up having a decimal after we've divided? Just reference that chart. Usually the only ones you're going to see are like 0.5, you'd multiply by 2. 0.33, you'd multiply by 3. 0.25, you multiply by 4. Usually it's only those 3 that I tend to see pop up very often. So the second part says, hey, calculate the molecular formula. So the molecular formula is going to be some sort of multiplier of this. So molecular formula equals our empirical, which is P2O5, times N. We need to find N. N is equal to molecular mass over empirical mass. Molecular mass is given to you. It's that big heavy one there, 425.7 grams per mole. Know that the bigger number should always go on top. Okay, smaller number will go on the bottom, so that N is a whole number. You would never want to put the smaller number on the top if you get confused on like what's the molecular and the empirical. As far as the empirical formula, we have to calculate the empirical formula. The empirical formula is going to be the mass of 2 phosphoruses and 5 oxygens. So it is 141.9 grams per mole. So let's take the big number and divide it by the small number. 5.7 divided by 141.9, and we get a value of 3. You should get a whole number. If you don't get a whole number, something went awry somewhere. Are we done? Yay, we're done. Not quite. Okay, we have to take that 3 and we have to thread it back into this equation here. So take the 3 and stick it in there, right here. So P will now have 6, O will now have 15. Big compound. So here's our molecular, here's our empirical. Any questions on that, on how those pieces all fit together? It's kind of an involved problem, right? It takes a little bit of time. So you may have just like one part of it or another part of it. Don't expect to have one that's like straight through like this on the test. It'd just be too much work for one point. So that is the end of chapter 6, finally. It's like such a long chapter. So we're done with that. We will be able to bail on Thursday. So I will see you guys next Tuesday. Awesome. So you have a nice long week. You still have stuff due though, all right? So make sure that you've got your test done by tonight. You will still have homework and labs due. You just happen to have all the information already. So you can go ahead and do the labs and the homework, today if you want to, because you've got everything. All right, awesome job. I'm gonna go to the beach. So you guys have fun. If you have any questions, stay around. General questions, shout them out. Personal questions, let's wait until I can take you in one at a time. Okay, otherwise, have an awesome week.
Thank
Hope you have a
you.
good fourth. Bye.